the guy that started down. That's Greg Paul. He probably finds it for Canvas. Yeah.
All right, finally ready to go. This is a nice sized crowd out. This is actually closer to what we expect from the RSVPs. Awesome. Yep, take your RSVPs, divide them in half. We're actually beating the RSVP count here, so that's awesome. So, welcome to Machine Learning and Data Science monthly meetup. This month we have applying ML to GPS data from Jerry Reed. We are the second Wednesday of every month here in the Iron Yard, and I believe we have someone from the Iron Yard who wants to say hi.
Hello, I'm Eric. I am the new campus director here at the Iron Yard, so welcome. I've been here 2 weeks, and this is my first meetup here. So thanks for letting me have that opportunity. If you guys have any questions, feel free to let us know. Phone number's up at the front door, some nifty little cards, and left you some stickers. So if you know of anyone that wants to pursue coding or that you think should, have them give us a call. 12 weeks, and they can get their skills up to the level of junior developer for full stack development. So that's it. But welcome. You can let me know, and I'm going to try to minimize my traffic in and out, but I apologize in advance. Thank you.
We love the Iron Yard. Everyone in Orlando loves the Iron Yard. All right, so I know we have a bunch of first-timers here with us, and a lot of people on the live stream who've probably never seen us before. We do, in fact, live stream. So everything that you do or say will be heard in one way or another. In this case,
YOLO.
let me take a step back. I'm Michael DuPont. I'm a machine learning developer out of my house, and this is my co-organizer, Casey. Works over at Food School. It's awesome. We do talks, projects, workshops. Really, it depends on whoever the speaker, however they want to organize it. We do encourage all of our speakers to have some kind of interactive component, sharing code so people can bring their computers to follow along. We touch on everything that you could possibly imagine in machine learning and data science. We've only been around this is our 6th one, guys. We've been here for half a year. Yay. If you're not on the Orlando Developers Slack, talk to one of us, talk to anyone who is. We will invite you. And you can find us on the Data Science channel, as well as meetups. I'm also on Python. Say what you're going to say. Oh, well, that's not a problem. And and like I mentioned before, we do YouTube live streaming. So if you can't make it out to the meetup in person, you can always check the live stream when it goes live. And by live streaming, we also have an archive of all of our previous meetups. So if there's a topic that you saw in the past, go to the YouTube page. They are all there, as well as all of the ones that we do with Orlando Python, because I'm also the organizer of Orlando Python. Speaking of Python, until it happens, I'm going to have the slide in here. I am the chair of organizing Florida PyCon, which is the first regional PyCon in Florida. The next nearest one is up in Tennessee. It's going to be here in this building. We're going to be using the Iron Yard, Canvas, the Central Atrium, and Power DMS to host everything. October 7th is the first Saturday. We are also kickstarting Orlando Tech Week. So there's going to be an event in here on Friday. We come in, Orlando Tech Week starts, and the end of Orlando Tech Week, also back in this space, is something we call Bar Camp, which is a conference, but there's no scheduling whatsoever. Whoever wants to talk comes in the morning, puts what they want to talk about on an open time slot, and you just go to it. It's really fun. FLPY.org is where you can get more information and where we will be posting information in the future. And as usual, I have a bunch of interesting links. I came back from the U.S. National PyCon last month and got a bunch of more Python-centered things. So Persimmon, Picasso, Deep Feature Flow, I believe all 3 of those are Python-centric libraries. Persimmon actually gives you a visual drag-and-drop interface for all of sklearn. It's really cool. If you've used Azure ML, it's like that except for sklearn. Picasso is visualizing your convolutional neural networks. If you want to see what each of the nodes in your neural network, your convolutional layers look like, this will show you. Deep Feature Flow is Django for analyzing video. It has a bunch of pre-trained models and will do things like road detection, object detection, and you don't have to worry about actually implementing them yourself. Apple, of course, had WWDC last week, and they announced a bunch of CoreML tools. Started playing around with that. I'm actually slated to give a talk on CoreML at the Orlando iOS meetup in August, so definitely come out with that. What more fun for me is they also have a library called CoreML Tools, which is a Python library to take all of your trained Python ML models, sklearn, Keras, TensorFlow, a bunch of other listed ones that I didn't even see and didn't know about, and convert those to be used in iOS and Mac applications. And then I also found a sizable repository of public data sets that Amazon is hosting. So if you're looking for a good sized data set, you can go into Kaggle or you can go to AWS and get some. And these, in the meetup description, I have a link to this slide deck with this slide here with all the links, as well as all of the previous month's links since I started to keep an archive of it. And now, the reason you all came out, applying ML to GPS data for Jerry Reed.
Shape here.
And I will switch this.
Okay, cool. Do you want me to stand over there? Or
No. Just getting the slides into the image
Slides
there.
will be better without me standing there, but I'll talk loud. So. Hi, my name is Jerry Reed, and I teach computer programming at Valencia College on the West Campus. And I've been interested in data science for on and off, and I've been fiddling with data science, let's say, for several years. And I thought today I would go through some of the little study I did with GPS data, global positioning data. Now, probably when you think of GPS, you think of the nice lady in your car who tells you how to find the Taco Bell, right? And maybe you are not interested directly in GPS because you know where all the Taco Bells are. However, I think by looking at the GPS data stream, and there's a lot of information in the stream that you can capture with really elemental hardware, you can find out some interesting stuff. So I decided to look at the way in which GPS is wrong. Because GPS is not really accurate enough to guide your car by itself. It's certainly not accurate enough for landing an aircraft. Why is that? I mean, why is it that what are the errors of life in GPS? And so I decided to take a deep dive into that, even if you're not interested in GPS, because you don't care about latitude, longitude, or Taco Bell. You may be interested in the way that we went through this data, because it sort of shows some techniques, some of which I would call classic, some would say vintage techniques for handling data, like a relational database. So, okay, hopefully this is we're off to it. Let's see. Nope. Okay, my experience with presenter mode here is rather limited in slides, Google Slides, so I'll do it this way. Okay, well, I changed my view, it didn't change yours. Let's try it again. Present from beginning, and let's drag it over. And what's the number here? Yeah, I'm open for some help here. Can you drag right? I think it's right. If you want to use your GPS on your phone to find a local Taco Bell, this would be a good time. So So I don't actually have to do this interview. I just want the slides to show. I suppose we know what I'm going to say. So you do this. Let's take that thing down and we'll go. There we go. Google's helpfully telling me if we can ask questions. Okay, now we go. All right. Thank you very much. Yeah. Okay, and that concludes my talk. I'll talk a little bit briefly about GPS, just in terms of overview, what it is and how a little bit about how it works, not much technical detail. I'll talk about how I acquired the data that I processed, because that involves a little bit of hardware stuff if you like that kind of Arduino, Raspberry Pi, DIY stuff. Yep. And I do. Got some of that. The data preparation and transformation, how I got the data from the GPS into the database and out of the database into P5JS. The data representation, I basically decided to put it in a MySQL database, a relational database, because it turns out it works that really nicely for this particular example. And there might be some dips in that. I took initial visualization using GNU Plot. There's a vintage piece of software. And then I did some stuff in Pandas, because Pandas makes it really easy. I mean, even I can do it, to do some simple visualization like ggplot, and to do some time series analysis, which I just basically looked at the errors over time, and you'll see what that looks like. And then I did a custom visualization. That's the part I really like. I did a visualization in something called P5JS, which is the JavaScript implementation of something called processing, which probably doesn't help you very well. But it's essentially a language designed for data visualization. It's a programming language designed for data visualization. And it makes it really easy. And I'll try to make the point of why I think custom visualizations are interesting and important over and above the visualizations you can get canned out of something like Pandas. So you can do some things interactively and see some patterns that are difficult or impossible to see in a series of static pictures. Talk a little bit about future corrections and show you a really ugly visualization that I'm still working on. So that's the plan. Two things about GPS are relevant to this presentation: accuracy versus precision. Accuracy is how close your fix, your known position, is to your real position, right? It's proximity to a known standard. And GPS there is different sources quote different accuracy, but 5 meters or roughly 15 feet is not a bad guess for where you are anywhere in the world, usually within a circle with a 15-foot radius. That's the accuracy of an absolute fix on the Earth. However, there's also precision, which is really about repeatability. And it turns out that fixes are a lot more repeatable than the 15 feet implies. I found this out, and I guess I could have figured this out, but I noticed it. I took a GPS, and I walked around a big square in a parking lot, like 50, rectangle, 50 by 100 feet. And I did it a couple of times, and in each case, I could come back to within a foot or so of where I started, over maybe a 2-minute walk, which is interesting given that you would think you might be 15 feet either way. So there's some repeatability there that's better than the absolute accuracy. We'll look at why that is, and when you look at the data stream, you can actually see what happens. So that's the plan. GPS errors, there are multiple sources of error for GPS, and they all kind of pile up, and they're not necessarily additive. From largest to smallest, and I got these off Trimble's webpage, they're a big manufacturer of GPS equipment. The Earth's ionosphere, which is the ionized layer in the Earth's atmosphere through which radio signals must travel to get from the satellite to your location. Since a large part of how GPS locates your position is essentially travel time from the satellites to your receiver, anything that affects the travel time affects your positional accuracy. So the Earth's ionosphere is good for maybe 15 feet of stuff, 15 feet of error. Orbit errors and satellite clocks, they're not perfect. There's absolutely nothing we can do about that, so we'll ignore that one because we don't control the satellites. Multipath, which is a phenomenon you get echoes off of buildings and nearby cars. You've experienced it if you try to get a cell phone signal in one of these urban canyons. You can't get beams for signal. If you think back to before you had satellite radio and MP3 in your car, you had an FM radio, those were the days. and you pulled up to a stoplight, and just as you pulled up, the station got really corrupted. But if you edged forward about 2 or 3 more feet, it came in clearly again. That's a multipass effect. That affects GPS, but it's a fairly small effect. The Earth's troposphere, which is the part we live in, the air we breathe, weather does affect the signal. But again, look, it's about 1/10 of the effect of the ionosphere. So most of these change slowly, which is the important thing. That's why it works as well as it does. So they may not affect successive fixes, successive measurements, nearly as much as you think. So I thought, maybe I could average these out. What if I set a GPS down in a known location and take 4 8-hour worth of data, average all the latitude and longitude? Gosh, it ought to be spot on, right? Because there's an error over here, there's an error over here, there's an error over here. There should be a central tendency. Turns out that's not true, and I'll show you why. So here's the experiment. There's the box that does not look like a bomb. It's covered with stickers because these days, this day and age, if you leave something out on the college campus, you probably should mark that it's not a bomb. You should call security and tell them it's not a bomb, and you should call the guys who mow the lawn and tell them it's not a bomb. So I made it. It's got an explanatory note. It's got my phone number. It's got a college sticker and some very cool crime scene type tape that I found at Home Depot. So I put together in the box, most of the box is a battery, as you'll see. Big battery, a Raspberry Pi, an Adafruit Ultimate GPS, which is the inexpensive consumer-grade GPS. And I set it down on a known benchmark, collected fixes 1 per second, because that's the data rate, for 4 to 8 hours. Then I wrote a program to average and show the fixes, and then I started digging into the data to see why the pattern was what it turned out to be. If you look inside the box, and this is definitely for the hardware weenies here, there is a huge battery, which is like a trolling motor battery, the kind of battery that you can run down and charge up and it doesn't die. This was a Pi 2, so it didn't have the built-in Wi-Fi, so I hung a little TP-Link travel router on it. That means I can stand outside the box with my laptop and start the program, stop the program, collect the data, those kind of things. There's the actual GPS. It's a little tiny. It's about an 1.5 by 1.5 inches. It's inside the box, so the box doesn't make much difference in the accuracy. And there's some power supply components to get from 12 volts to 5 volts. So, other than the fact it weighs about 30 pounds, it's how to carry, works pretty well, and it's absolutely waterproof in my wonderful Walmart battery box. So, the only thing I bought at Walmart in the last 5 years was a box. That's the GPS, not to scale. As I say, it's about the size of 1.5 inches by 1.5 inches. The actual GPS is this little cube here, and the antenna, believe it or not, is that thing. It has a connector for an external antenna, which is cool if you want to mount it somewhere where it can't see the sky. You can run a wire out to the external antenna or put it on top of your car and get better data. And of course, it's basically just Adafruit has soldered this down for you and pinned it out so you have easy connections for power, ground, and the data that the GPS spits out. So it's really easy to use. Costs about $40, I think. So an inexpensive consumer-grade GPS. Now, I needed to find a known location, a location whose accuracy was known. I thought I needed to know like the inches. So I started out trying to find that. It turns out that is its own side trip because finding a well-known and accurate benchmark is not easy. There is a browser, and if you go to the National Geodetic Survey and you put in your zip code, they will show you all the benchmarks that have been set over the years in your locales. This is Apopka. And notice that they're almost all along the sides of roads. There comes the problem. So I set out to find some of these. So I found this one. I thought, oh, this is convenient to me. It's right in downtown Apopka. Well, it's currently under a Jiffy Lube, which is particularly an ignominious fate because Jiffy Lube and I don't get along since they stripped out my oil pan. So covered up by concrete. There's one up here that's under the 429. There's one up here that's under a church sidewalk, and so forth and so on. Most of these have been destroyed by progress. The one that's under Jiffy Lube has been in Apopka since 1930, and now it's under the Jiffy Lube. So, okay, well, I figure, what about these up here? I mean, this is in the middle of nowhere. It's like up in the woods. Maybe I could find one of those, right, and put my box on it, and nobody thinks it's a bomb up there. So I thought that was pretty cool. So then I started looking. They tell you how to find the thing. There's a description. The last time this one was found was in 1990. And I won't, this is an eye test, I know, but I'll give you a little bit of it. Turn right and pass through the gate. Proceed southwesterly along the sand trail to a fork in the road. To the left at 0.2 of a mile. Continue southwesterly to a hunting camp at 0.3 miles. Proceed southerly through the camp to the left of a twin oak tree and past a motorhome parked on the rock. I just don't think I'm going to find that. And driving through a hunting camp sounds like a good way to get shot. So that benchmark's not going to work. So luckily, I found on the Valencia College West Campus are some benchmarks that were set there by a surveying professor a number of years ago. And he was something of an old curmudgeon, but he was a good surveyor. And he set these points to an accuracy, I believe, of inches. I sort of confirmed that by looking at them on, this is a crude technique, looking at them on Google Earth. And you can actually see the white concrete around some of these if you zoom in enough on Google Earth. And if you put in the longitude, calculated longitude and latitude of that point, it appears to be right under the little pink marker. So I think it's spot on. So now I have known location. So I'm going to set my GPS on that. And up there between the two orange cones, thank you security for putting orange cones around it, which makes it seem less like a bomb, is the box. And it sits there for 8 hours and collects data. Right? So that's how I got the data. Well, perhaps an unnecessarily long story. Here's how the data actually gets from the GPS into a series of files and ultimately into the database. If this looks kind of like a mainframe-ish data flow architecture, it's probably because that's what influenced my formative years. It comes out of the GPS in a format called NMEA, N-M-E-A, National Marine Electronics Association, which doesn't matter. It comes out in CSV, which is very cool. It's very easy, a standard, well-documented CSV format. I love CSV. It goes into a piece of software called GPSD, the GPS daemon, which is running on Linux, and which transforms, it handles all of the nasty business. This is a serial data connection here at 4800 baud. So this handles all the nasty serial handshaking and stuff you definitely don't want to mess with. And it converts the NMEA CSV stream into JSON for you. It comes out of GPSD in a JSON stream. That's kind of handy. So I just pipe that into a text file. So now I have a text file full of JSON, 1 fix per second. The easy stuff. Here's what NMEA looks like. Let's see a sample. You don't have to be able to read it from there. There's a command word here that tells you what kind of sentence, they call them sentences, it is. There's a checksum at the end if you're really paranoid on a local USB connection. I didn't think it was worth checking. That's what comes after the star. And a series of comma-separated values. I've highlighted a couple. This particular sentence, the GPGLL sentence, has latitude and longitude in decimal degrees. They moved the decimal point over. It's times 10, times 100. I'm sure why, but probably get more precision. And there are other. You'll find that comes out in a couple of different. So this must have been 1 second. This must have been another second. There also are records that tell you how many satellites are in view, and they calculate something called dilution of precision. There's a wonderful term, dilution of precision, that has to do with the particular geometry of the satellites. Some satellite geometries are better than others for getting accurate data. Turns out, looks like from my preliminary analysis of this, the satellite geometries were always pretty good. So that's not going to explain what you see. So that comes out of the GPS. That goes into GPSD. GPSD spits this out, which is, notice it's got a couple of different objects, classes. Sky, which contains a lot of attributes about the satellites, and TPV. I can't remember what that stands for. It's a fix. It tells you where you are. That's the one that's got the latitude and longitude. Also, if you're moving, it has your heading, it has your speed, and it has your pitch. So which makes a lot of sense for vehicles. If you clean this up a little bit by putting it through a Prettyfire, you can read it, and you can see here all of these dots are dilutions of precision, horizontal, vertical, so forth and so on, for every satellite. And I just show one here because I ran out of room, but there's like a fix might have 20 satellites in it. there's a satellite identifier, and there's the elevation and azimuth of the satellite in the sky, which is kind of interesting, and a measure of signal strength, and an indicator of whether this particular satellite was used in calculating the position or not. So there might be many satellites that the GPS can hear that it doesn't use. This is the fixed, the TPV, and that's got primarily a timestamp, good to plus or minus 1 second. There are ways to get a lot better time on GPS if you need. A latitude, a longitude, an altitude, which is subject to a large error. A track, which is a bearing. A speed, which is a velocity. A climb, which is a pitch. And I don't remember what EPS is. So every second, you get all that stuff. So that's a lot of data. But it's interesting to look at, if I look at successive fixes, after I get this in my database, how do they move around over time? So, okay, so I got the JSON now. So again, following my mainframe-ish architecture here, from one file to the next file to the database, a tried and true technique. I read the JSON in with a Python program. You'll look at that in a minute. Those of you who are expert Python programmers will shudder. It spits out CSV again. So we went CSV, JSON, CSV. Not an elegant solution. And then you'll love this, I split it up into multiple CSV files. You'll see why I went back to CSV in a minute. I had a grand scheme to dump this all in a Mongo database. Seems like a good idea, right? JSON in, Mongo's built around JSON, but I ended up doing it in a relational database. So this is just processing along the way. Let's look at the program briefly. And it's pretty straightforward. And of course, I'm going to wrestle with dragging this over to the right. There we go. Hey, I'm getting good at this two-screen stuff. Okay.
Hit Command plus.
Yep. And let me get the right file up here. We want to look at okay, I can't see it well enough to see my titles at the top, but it should be. I have. Yeah, okay. I want this file, read gps3.py, which should be open up here, but depending on where I put it. Okay, suggestions?
Command T.
Yep. Thank you. Okay. It's basically, I made one class for each of the classes that appear in the JSON, right? And I made an additional class because in the JSON, the sky, the attributes about the satellites are all together. And I split the satellites out into their own file, you'll see, because they want to be their own table. So all this does is read it, and there are a couple of variations here. This as CSV just simply writes it out as CSV, as you might expect, as you read into a dictionary. Originally, and you'll see some comment out coding here, originally I did a bad thing, which was I wrote this out. There's three ways, at least, to get data in a database. And they differ in how slow they are and how easy they are. An easy but incredibly slow way is to write out SQL insert statements and then run the SQL insert statements. That takes about an hour to load 8 hours worth of data. It's convenient, but it's ugly. Another way, which is the elegant way, probably should have done it, is to use an API directly into the database. Python provides wrappers for those like SQL Alchemy that would allow you essentially to direct your program to directly insert the database. But there's a third way, and of course I went for that way. Write it out of CSV and load it in with a utility like Mongo import. The advantage of that is Mongo import will load the data in like that. It's really fast. Most databases have some kind of side utility that's designed to load data, and they're generally optimized for speed. Oracle has it, MySQL has it, and works pretty quick. So I ended up, as CSV, the advantage of getting a CSV is I can use that technique on it. So this is a pretty bad Python program. But it's object-oriented, so, you know, we hit one criterion. And I split out the TPV into two classes, a fix and a satellite, because I want them to end up, like all relational databases, as separate entities in the database. Okay. Let's get back to okay, so what the bit does, it eats JSON and spits out CSV. Okay, the SQL insert statements, bad idea. I guess I knew that, but what the heck. The result is you feed it into the MySQL import utility, which will suck it into MySQL, put it in the tables for you. It's really fast and easy. It's a pain to use the utility, but it's fast. You end up with this. And this is why I did it as a relational database and not a Mongo database. When I looked at the data stream, I realized this wants to be a relational database. It's got obvious relations. Fixes, skies relate fixes and satellites. So every position fix has a sky, it has a constellation of satellites. And every constellation of satellites has satellites. So you can make this a table, and this a table, and this a table. The relationships are really obvious. And you can join them, you can do queries against the individual tables, you can do lots of extemporaneous queries in SQL. And that's really, if you know SQL, that's really the advantage to me in a lot of ways, is the ability to query these tables and explore the data without having to do any further programming, just doing SQL. So that's the ER diagram for data. We can look at the tables with some small difficulty. Let's look at the mouse this way. Hey, I'm getting better at this. Something. This is, I assume, who here has not used SQL? And is honest enough to raise your hand and volunteer. An audience. Okay, great. So this is basically just a query that's going to find, let's find out the minimum, the weakest signal, the maximum signal, and how many satellites. So it's pretty easy to do. Just grab this. It'll take me longer to highlight this than it will to do the query. And we drag this window over. Hold on. So basically, the minimum signal, these go from like 0 to 50. The worst signal ever was like 16 or 17. The maximum signal is 40 something. And the minimum number of satellites for a fix. Every fix had at least 12 satellites. The theory just needs 6. So this thing had a pretty good view of the sky, right? Because you can see lots of stuff. There are 40 some odd satellites available, I think, at a given time. And you can do lots of extemporaneous queries like that if you want to find out interesting things about the data, either from individual tables or joining them together. So putting in a SQL database had the advantage that just off-the-cuff kind of queries were easy. Easier than navigating here. And okay, now I've lost again. Let's take this. Okay. Here's what you end up with after. Sorry. about, this one's off. I'm going to zoom this in a little bit. I can't zoom in much. Here's where you saw the orange cones. Here's the point that is between the orange cones. This one's off by about, after 8 hours of averaging, it's off by about 8 feet. This one, which I didn't show you the data for, is 4 hours of averaging. It's off by about 10 feet. So averaging doesn't do it. Something's going on. It obviously isn't just a random error. Otherwise, 8 hours of averaging would certainly have put this point in the Google map right on top of this point. So, Well, this explains it all very well, I think. This is the ball of yarn post-cat graph, which is a terrible, this may be a candidate for one of the worst charts ever made. And I say that shamelessly. This, of course, this is longitude, not latitude. So, and these numbers down here are essentially uninterpretable. However, what counts is the shape. The black dot is the centroid, the average. But look at the variation. Yeah, there's some heaping up in the middle, but there's some excursions out here way out. So something's happening to the data that's biasing the average, because the average turns out is probably not in the right place. That's the calculated average. That's not actually the benchmark. So having looked at that, I looked at that early on, and I never fixed the graph because I started looking at the data just to see how can you get something like that. So I decided to look at it with a better tool, the GNU plot. Although that graph is not GNU's plot's fault, that's my fault. So we can look at what I did in using pandas, this is actually the first time that I used pandas. But having heard about it here at Data Science, that was very cool. So, let me get over here. So I imported, one thing that always confuses me I imported a whole bunch of stuff, which is probably a beginner mistake. So I'm not sure what I actually ended up using in some cases. But it looks like matplotlib is what I ended up using the most. Pandas gives you a data frame, R-like data frame in Python, which is kind of cool. You get basically a dictionary with a lot of metadata in it that makes it easy to use. So I also imported autocorrelation, which is when you can take a time series and you look at how the time series relates to itself. So correlation is basically a similarity measure. So you correlate something with itself, it has a perfect correlation. But if you shift by one sample, 1 second in this case, and you correlate, and you shift by another second, you correlate, you get a measure of how self-similar the series is at different offsets. And this one has a pretty obvious effect. So I basically did it. You see, there's not much code to do this. That's the nice thing about pandas is that it's just 4 or 5 lines of code to produce these analyses. So let's look at the actual analyses. That's what the latitude looks like over time. That's actually latitude, again, it's not labeled very well, but it's 28.52005 and so forth and so on. And this is time in seconds, 25,000 seconds. And looks pretty random, right? So if you look at longitude, it looks pretty random. But that doesn't tell you a lot. I mean, it doesn't tell me how I got 8 feet or 10 feet off, right? Some combination of those. I looked at the autocorrelation function. These data are heavily dependent on one another. In other words, there's a huge dependency over many, many seconds between successive observations. That means they stick together. They don't bounce around randomly in a random walk. They tend to land in the same place over and over again. And if you want to see that very clearly, this is the partial autocorrelation. So ignore the first point here. This is the correlation of the series with itself. That's one. But the next second is almost as highly related to the previous second as the previous second is to itself. So, and if you know this one, if you know the previous sample, there's nothing else worth knowing. Just predict have your machine predict that the next sample will be right next to this sample, and that will work. So that's why the data move around in a non-random walk fashion. So, but I wasn't satisfied with that because that's not very, doesn't give you a very good intuitive feeling for how this happens. So clearly there's a bias in the location. Even 8 hours, averaging doesn't give you the true centroid. Time series looks like the fixes are successively related. So let's look at how they unfold over time. And that's where the P5JS program comes in. Now I started out in processing, and this requires a bit of that. Processing is originally a front end to Java. Processing is two things. It is an API, a graphical API, a simplified graphical API. So if you want to draw a rectangle, it's a single function call. You don't have to instantiate a canvas. You don't need an event listener. You just say rectangle, X, Y, Z, high, Y. So it greatly simplifies things. Originally it was in Java. It's now been ported to JavaScript. And when it's ported to JavaScript, that API is called P5JS. Processing is also an idiom, or what I'm calling an idiom. In other words, it's a way of writing a program. It's a way of writing an event-driven program that's always the same. There's a setup method that's run once and only once. In JavaScript, it's a preload method because if you want to read data, and JavaScript's completely asynchronous, you want to be able to get the data in before you start trying to draw it, you do it in a preload method. And it simply uses promises or some other mechanism to wait for the data to be loaded. And there's a draw method, which is really an event loop, which runs continuously, has its own event listener, and handles either mouse events or anything that needs to be done repeatedly. And all forms of processing, whether they're in Python or in Java or in JavaScript, use this same idiom, same way of setting your program up. It's like a design pattern for an event-driven program. This code loads data from the local file, which I've only found one browser that let me do that, because it's considered a very bad thing, of course. You really don't want your JavaScript programs to be mounted in local files. But Firefox on the Mac will do it, at least until some upgrade comes along. So let's look at the code for this thing, because this, I think, is interesting. And let's look at this one. That's a simulation. Let's look at this one. So I actually transliterated this from Java to JavaScript, which was surprisingly easy given that I know crap about JavaScript. It's probably not very good JavaScript, but it was an easy transliteration. I have a bunch of variables I had to compute. Mostly I computed to make a reasonable graph. I've got the real location of the benchmark, and then I just computed what's 30 feet one side of it, 30 feet the other side of it, 30 feet north of it, 30 feet south of it, make a frame. And here, if you need to do something, so I have a minimal user interface, you'll see how minimal it is, which is this mouse press function, which is easy. I have some sound, which turns out to be really easy. There's preload. All that does is load in the data that I extracted from the database. So when I found the data I wanted, I just spat it back out in a CSV file. You may start to see a pattern here. Lots of CSV. Setup does the one-time stuff like creating a canvas, set the background to black. Yes, that's very uninventive. Parse the lines, which is all these methods are, this is a method that comes from processing, this. These all come with the processing API. So basically you just load that in your HTML file, you load in the P5JS libraries, you get all that stuff for free. And I use the map function, an extremely handy function that's available in most languages, to rescale the latitude and longitude so they fit on a screen that's 500 pixels by 500 pixels. Very handy function. Yes, you should be able to just sit down and write that function. Every time I've tried to sit down and write that function, I messed it up, so I use theirs. And if you want to draw a shape in processing, you select your fill. This is hue, saturation, and brightness. You can work in RGB or HSB. And then I draw an ellipse, which is a circle, actually, at this location. So it takes just a couple lines of code draws something, which is nice. Having done all that setup, once the program runs, it drops into the draw method. And the draw method just takes successive lines from the input file, parses them, and draws them on the screen, throws them up there. And I draw it kind of what I thought was a cool way. We'll see what you think, because it looks a little better than just points. And all this code is just devoted basically to drawing a line and then drawing previous lines and then erasing them again. So let's look at what it looks like when it runs. Here's what I thought the data would look like, right? I said it'd be a random walk. So I made a simulation, and so drag this over. Oh, hooray. Yes, the north, south, east, and west cardinal points are not aligned correctly. That's because I can't count on my fingers well enough to get half the width divided by 2 plus half the width of the character, blah, blah, blah. But they show you what you need to know, right? This is north, this is west, south, and east. That's the benchmark. If you start this running, this is what I thought it would look like. I thought that's a random walk. That's a Gaussian distribution of points, right? With a centroid that's here, and they're all over the place, but very quickly it converges to be, you're out 13 minutes, you should be right on the benchmark, right? Should be right on. And so everything beyond like 20 minutes is overkill. This is not what's happening, because we end up with a bias. It doesn't converge, and you'll see the pattern doesn't look anything like that, because those are all independent. And the one thing we know from looking at the pandas output and the autocorrelation function is that these fixes are not independent. If you look at this one, this is the actual data. Now, this is the real benchmark. This is the first measurement, which was way off somewhere. And this is the point they will eventually converge to. It's about 8 feet wrong. You'll see this point move as the data comes in, because I compute. This is like a running centroid. This is the real point. This is a running centroid. This is the value at the end. If you run this, it has a completely different shape. I made the little stroke thing there because I thought it looked cool. It does show you one thing. It shows you where you've been. So it leaves a trail. It shows you where you've been. And all what's happening is the stroke goes out to wherever the point actually is. So these are landing up here. And this point will start to move when you get enough data. And so we're 24 minutes out, and we're not even close to the center, right? You get a lot of points. Notice it doesn't move for quite a while. That's because all those fixes are landing in the same place. The wrong place, but the same place. And if you watch it long enough, which well, that's what we do here, it never goes over here. Never goes in that quadrant. So that's the bias. That's why you end up, you take a big excursion down to the southwest, but you never take any excursions to the northeast. So given the vagaries of the ionosphere that day, I suppose, that's where the fixes will land. But notice from one to another, they're pretty good. So if you want to fly your drone or drive your little autonomous vehicle, you're probably good over a short period of time to within a couple of feet. Even over the long term, you're going to be way off. So this is something you can do dynamically that you can't really do with a static graph. You can display the data in speeded up time, which is kind of cool, and see where things, how the data actually got the ball and yarn shape. These data won't get that same ball of yarn shape because these are from a different trial, but the same idea. Every one of them is different. Okay, well, I thought of another couple of twists here. I'll show you one of them. I'll try to show you one of them. Yeah. That's what I thought the data would look like. That's what data actually looked like. You saw it, right? You can also, and I got this is purely Flash, but you can also listen to the data. I like the idea of an auditory visualization. I mean, that's the sort of oxymoronic thing that appeals to me. Let's look at the, that's a different kind of scrolling. That's the old school scrolling there. Right, let's go here. And let's go back to, where's my Firefox? Here. And okay, here's the random one. We'll stop that. We'll reload it. And let's try this. Let's try turning on. There it is. The effect you heard every science fiction movie when they had telemetry, right? But notice, because it's a random series of notes, right? It's completely random. So it sounds like, I don't know. However, if you do this one, reload this one, turn the sound on. Let's see, yeah, hey, there you go. If I'd had time, I would have done it on a musical scale, but I didn't have time to do that. The sound data you got is very cool here. Very easy. This is just audible. The lower the frequency, the closer you are to the centroid. So here, it's like a beat note. But if you, the original one I modeled is the one actually took a musical scale and played the sequence of notes. That's a pretty bad music. Well, wait one second. It'll pop over here in a second. It's a little more exciting. We'll give everybody's ears a break. There we go. There's a nice riff, if you can call it that. Okay.
Interesting.
So actually, there's a really neat podcast where they do that in a meaningful way, which is there's a podcast where an astronomer explains how you can listen to gravitational waves. And the LIGO, laser gravitational interferometer, actually produces, the gravitational waves produce a perturbation in the lasers that is at an audio frequency. And so he actually has audio of the gravity wave they detected in LIGO. So that's a cool podcast. So mine is not nearly that profound. There's a lot more data to look at in the future. I'll show you a really awful visualization. You should respect the fact that I showed you some terrible visualizations tonight. So I should, I held nothing back, for better or for worse. This one's in processing the Java version. That's what processing looked like for a long time, still looks like. It's got its own little IDE. You can do it in Eclipse if you want, but it comes with its own little IDE. And you can see it's got the same sort of functions in the API that I'm using in the JavaScript one. The JavaScript is a port of this. So you can load a font, you can load data, you can load strings, you can draw stuff. This one shows, let me drag the window over. Oh, that was good. All right, well, let's reopen it and see what happens. I think it doesn't understand dual monitors. I have a terrible feeling it doesn't understand dual monitors. But let's see. You won't be missing a whole lot in this visualization, to be honest. Open recent. Let's see.
Sometimes they fork the processing UI to create the Arduino IDE.
Yes, and several vendors then fork that to produce their own proprietary version. Texas Instruments has a version for their chip. It's just like Arduino, but it's red. Because everything TI does is like Verizon is red. So yeah, it's open source. The IDE is a Java IDE. It's open source. So everybody picked it up, and they also took the metaphor, which is kind of cool. I do like the sketch metaphor. The idea that you're not writing a program, you're writing a sketch in the sense that an artist writes a sketch, because it kind of gives you, yeah, every now and then the sound comes through, it's muted. You're writing a prototype. You're prototyping. Like an artist sketches something before, he or she makes a sculpture. I'll try one more time, but I think this is going to blow up on 2 monitors. Maybe not. There you go. Space caterpillars. Can I get an ew? Ew. Those are actually satellite tracks, because remember, what's in the satellite table is the azimuth and elevation of the satellite is viewed from your location. So I've shown. Now that's flattened out it needs to be 3D and it needs to be on a sphere. So it's pretty horrible because it's a flat view of 180 degrees. But skyworms. But at least you can see it. The size of the dots is proportional to the signal strength at that point. And you should see. Notice how the ones that are near the horizon are weaker because they're fainter, and the ones that are high are brighter because they have a stronger signal. Because the satellites also tell you how strong their signal is. So that may be fun to play with. I've seen a really cool version of this. The guy in Germany did. But it's static. It's not dynamic. But he's got a picture. He tracked GPS satellites over his real horizon, which is a picture of his panoramic picture of his real horizon, and superimposed them. So it's kind of neat. So I'd like to do that with my horizon, but I'm not anywhere close to that. So anyway, that's like a future direction, and obviously it could be some improvement. Let's see if I can get here. And a couple takeaways. So basically, consider relational models. I mean, I spent a lot of time playing with MongoDB because it's interesting. It's completely different. It's completely non-relational. It's basically a JSON store that's highly scalable, and the query language is JavaScript. So if you like that, that's cool, a JSON JavaScript. But if you have data that fall into a relational database, you don't have to contort them to make them relational, you should do that because it's a lot more flexible. If you can dump everything in the world into a Mongo database, because every document, that is every row, can have different attributes. If you do that, and then you decide to do some query that involves, God forbid, joining 2 collections together, you'll find it's very difficult and very efficient. That's something that relational databases do well. They're very good at putting large amounts of data together and essentially match merging. So use the tools you know best. I say this in my own defense. If you can write a custom program, which a lot of what I did there in a pretty horrible series of pipelines could have been done in one nice Python program, then do that. But if you're in a quick exploration, use the tools that you know how to use, and the command line tools for me were the fastest way to get the job done. And you can dump those all in a script. I could take another series of measurements and produce that same thing again with very little time. Do the quick and easy static visualizations and analysis first. Pandas does that really well. You see, it took me literally 15 minutes to get those ugly graphs I showed you, really quick. And that includes some Googling, but I couldn't figure out how to do it. But don't underestimate the power of writing a custom visualization. You can do some things in a custom visualization that you can't do with a bar chart or a line chart or a scatter plot. And I say, look closely enough, and you can find interesting things, hopefully I convince some of you of that, in the apparently mundane, like a series of latitude and longitude. So, questions? Yeah?
How many trial runs?
You saw a trial number in there, right? I love the trial number 5. So 4 was the one, remember the picture that showed all the stars on the Google map? 4 was the one that was 10 feet off down the sidewalk. 5 was the one that was up by the pine trees. 3 and 2 were in my yard.
Have you ever ran the duplicate trial at the same location?
No, I'd like to do that. That's a good future direction because I bet you on a different day, even in the same location, you would get a different distribution of fixes. Because the ionosphere, the primary driver of the inaccuracy, is going to change slowly from day to day. There also might be some kind of solar effect on that too. It'd be interesting to try to correlate that with the solar alerts you can get off the web.
Is the data set available?
All this stuff is dumped on my GitHub page. You're welcome to take a look at it, including all the data. It's not very neatly organized, but it's all there. Other questions? Yes.
Just a question on the P5 library that you use.
Mm-hmm.
So, like, as far as like other tools, did you consider any other visualization? Like, so like one of the things that we did in school is D3, and I'm seeing some similarities there.
I've heard D3. I think D3 is JavaScript based.
It is JavaScript.
Yeah, I haven't used it. I used the processing one because I was familiar with processing.
Right.
So I thought, I know that API, I know that idiom. Having it in JavaScript is just really cool. So, I can show you the P5.js page, which is also kind of neat. They do a really nice job on the page. Let's see if it's over here. Actually, this is my favorite podcast, by the way. Data Stories. These folks do visualization. They don't really do machine learning or data science much. But they have like artists and they have all kinds of stuff. And these guys, Enrico Bertini and Moritz Steffner, I don't know if you are familiar with the old Saturday Night Live, Two Wild and Crazy Guys sketches. These guys sound like that. They're incredibly enthusiastic. They're heavily accented, and they're just having a great time. And they interview really interesting people. It's a great podcast for just like driving along. If I drive along and I listen to machine learning podcasts, I have a tendency to like run red lights and stuff. I'm thinking about how does that work? But these guys are talking about their careers and their visualizations they've created and the guests have created. Much easier listening. I really like that. Let's see if I can get you P5.js up here too. I can't type it. P5.js. And I'll try to get this up so it's a little bit easier to see. Kind of a nice interactive graphic. They change the graphics every now and then. I like the one they had last week. They had these little like paper doll figures, and they would randomly jump and take off on some trajectory. Didn't symbolize anything, but it was kind of cool. And if you look at their reference, this is all the methods that they've imported over from Python. And, oops. Well, that didn't load too well, did it? I'm not sure why it didn't load. Since I was looking at it not very long ago. But basically, they have everything you see in processing.
Quick follow-up question then.
Yeah.
It ran very quickly. So how much data were you loading at any one time in the was it
There's 25,000 seconds or something, so it was chewing through that in a few minutes. Probably. I was just surprised. I expected it to be really slow. But then again, the original processing is Java, so JavaScript's got a sporting chance to beat Java. We all got a sporting chance to beat Java, right? The other thing is, if you are a good JavaScript, HTML, CSS person, you have the possibility of embedding this kind of stuff in a real web page instead of just kind of a black square, and you can make some nice stuff. Yes? Mm-hmm.
So, what's the objective of
The objective of this was just, I was morally curious about why my GPS fixes were the way they were, why they were inaccurate on the long term, but accurate in the short term. And I just wanted an example, which I actually use with students, of how you might drill down into that kind of data and make a visualization. So probably some model project.
Have you considered perhaps
I'm sorry, say again?
have you thought of a way of helping increasing the accuracy?
Yeah, that's the whole topic in itself, and there are ways to do that. GPS has a couple of ways to do that. First of all, for military GPSs, the GPS satellites transmit on 2 frequencies. There's much better if you can receive both frequencies and decrypt both frequencies, so the military one's encrypted, then you can use the difference in arrival times of the two frequencies to estimate the ionospheric propagation delay and correct for it. There's also the scheme that there are correction signals transmitted over satellites because ground stations with known locations uplink to the satellite. Oh, you say I'm here, but I'm actually here. And those corrections are retransmitted from the satellite to your GPS, unfortunately not to my GPS, to correct the fix based on the current state of the ionosphere within some locality. There used to be actually transmitters, ground-based transmitters at the entrance to harbors, for instance, that were used called the wide area augmentation system that was used to improve GPS fixes, where you might run into a ship or a sandbar or something. So there are definitely ways to do it. I thought, what if I put one GPS, because these are cheap GPSs, and I got lots of Raspberry Pis, put one of them on one benchmark, and I put the other one on the other benchmark, and I use a Wi-Fi link between the two GPSs. Could I send my own correction data over from GPS A to GPS B and get tighter fixes on B? So that would be interesting to try. So there are definitely ways to do it. The surveyors do this differential GPS. That's basically what they do. They put a transmitter on a known location, and then the mobile one, when you go out to the unknown point, it not only gets the GPS fix of the satellites, it gets the correction signal from the local GPS that's over the known point. All of surveying consists of going from known points to unknown points. That's the whole principle of surveying. Other questions? Yeah.
Did you look at the individual satellites? Is there ever like one that's just wrong, or like is there?
I haven't, but that is a really good question because you think if it really wanted to turn it off, but on the other hand, I don't know. There are a couple of satellites that transmit these corrections. The ones with high numbers, like 138 instead of like 1 to 50. But my GPS says it's not using those, so I'm not because I guess for $40 you don't get that. There's a lot of calculation involved in using the correction signal. I think there's not enough horsepower in the onboard processor on an expensive GPS for them to effectively make that. GPSD claims that if your GPS will do what they will enable it. The other thing GPSD does for you is to hide manufacturer to manufacturer differences in GPSs and give you a standard JSON interface to a GPS so you don't have to know it's a Trimble or it's a Garmin or it's a God knows what. And they wax poetic on their page about all the ugly differences that exist between GPSs. So they've convinced me that I want to use their software. It's an old piece of software. It's been out for a long time. It's very reliable. Any other questions? Yeah.
In your presentation, you talked about collecting the data and visualizing. On the description of the where it says that we can use machine learning to improve the result accuracy of these devices.
I didn't do that, but I believe it would have to do with the sort of differential scheme that I was saying. Because they're highly intercorrelated, but that doesn't necessarily enable you to make a better, that if it's here, it's likely to be in a very small circle, but it doesn't really give you the ability to predict. The time series, it looks predictable, but it's not actually going to help you much, I don't think. I think you need an external source to improve beyond what you can get the way I did. My original scheme was averaging. I thought averaging would do it, and I was wrong.
Oh, okay.
Averaging gives you a biased estimate. It doesn't, because the errors are non-randomly distributed, and because they're highly intercorrelated, averaging doesn't do it for you. A random walk, as you saw, like in 10 minutes, you'd be spot on. It doesn't work that way. Other questions? Yeah.
How would you inform a beginner in data visualization to go about learning data visualization?
I think, first of all, there's some pretty good books on that. I'm trying to think of there's a data site, a website called Flowing Data. You familiar with Flowing Data? I'll bring that up. Nathan Hugh, I think, has written a number of books that I highly recommend. He mostly works in R, but a lot of the stuff he does is language independent. And He's got a couple of books out, which I'm sure you can find on the page here, that are very good on data. It's heavy on visualization, not so much on data science per se. Data science per se, there are a number of good books that talk about data science in terms of Python. It's like Data Science from Scratch, I think. I don't know if you're familiar with that one. That goes through a lot of very low stuff, talks about how gradient descent works, talks about some mechanics of it, how generators differ from dictionaries and so forth and so on. So because you might want to use generators, you have large data sets and dictionaries become infeasibly large. So I think it's called Data Science from Scratch. It's an O'Reilly book. That one's pretty good. There's also a couple of similarly named data science. One's the VM I've used that you install it and it comes with a whole bunch of data science tools pre-installed. I have to research the name for you. I can't remember what the name is.
Couldn't be ran on VMware, for example.
Yeah, or on VirtualBox probably.
Something else that you could look at is the best way to learn how to do something, and especially when it comes to data science programming, is just to pick a project and do it. I'd recommend getting a known clean data set, either out of a native R install or off of Kaggle, so you know that you're working with known clean and usable data. And then then to get a feel for the data, you can load it into Plotly comes to mind as a really good website. plot.ly. It's a free online tool. You can import your data, and you don't have to worry about actually coding it. And then once you get a couple of graphs that you say, this is really good, I want to learn how to make this in code, choose your language, find a well-supported visualization library, and then see if you can replicate those visualizations in the program.
And again, my personal favorite is processing in its many variants. I haven't done much with the Python version, but that looks pretty cool too. So it's basically the processing API in Python. So I like the API because it's easy to use to get graphical, low-level graphics. If you want charts, use Pandas or one of the things associated with Pandas. If you want to draw your own lines and boxes and circles, like I did, then definitely use the processing API. Makes it really easy. And there's some processing actually came out of data visualization. The guys who wrote, the two individuals who wrote processing originally, Ben Fry and Casey Reyes, were students. They were students at MIT in Tufts data graphics program, and the original use was in human genome, the first human genome visualization. Fry worked on that. So those guys came out of that model.
You teach some years at Valencia.
I try to work this into, I don't have a data visualization class I teach. I try to work it into my other classes because I think it makes great examples for students to do. And I think it's really, it gets my interest. I don't know if it interests the students, but at least it gets my interest. And I'm enthusiastic. And I think it base some of that. Because if I'm bored with it, it's really not going to work. And if I don't see that C program to search for keywords again with stir, it'll be too soon. I never get it. So I'm running out of, and those I'm trying to inject Arduino examples into. I'm just sick of C. I worked in C for many years, and the only C that interests me anymore is embedded stuff. And that's the only C that exists anymore, really. Is in the embedded world. Besides which, if you want to do C, you should just do C++ and forget C. They've gone together and never separate. There's no pure C anymore. It's all C++. Other questions? Thank you very much.
All right, very fun. So thank you so much, Jerry, for filling in on short notice. We had a visiting speaker who was going to be here this month, but plans changed. We'll see what we can do about getting him in the future.
Yeah, I'd like to hear that spark.
Oh yeah, he was going to talk about, he works at Databricks, and was going to talk about using Apache Spark with Databricks. Check out Databricks. It's if you've heard of Beaker.io, it's very similar. Or take a step back. If anyone has heard of Jupyter Notebooks, there you go. More people have heard of Jupyter Notebooks. It's a wonderful way to mix in Markdown and code blocks together, so you can share and do more scientific workflow. Beaker.io, Databricks, these allow you to take that concept and mix different languages in your data blocks, and they all share the same variables with each other. So if you need to mix SQL to read in a bunch of code, you can have an SQL block, and now your data that you pulled in with SQL is now available, so you can pull out it. You can do some data formatting in Python, and then do your data analysis in R if you want, and mix in comments about what you're doing the whole time. So definitely check those kind of sites out, Databricks.io and Beaker.io. We'll see what we have about next month. We're thinking next month maybe we'll do more of a mob programming kind of thing.
If someone's got headphones on at home and their ears are bleeding out.
We're gonna see about finding a tutorial about some kind of advanced ML concept and trying to improve upon what the tutorial has. So we'll find something. If you find something that's really cool, send it our way. You can get to us on the Orlando Dev Slack, Data Science channel. You can always message us over Meetup. Any way that you can get to us, send us something cool. We'll have that for next time. Also, Orlando PyCon Florida PyCon going to be here in October. I just created the next Orlando Python meetup. We're going to look at a library called Pug, a Flask-like implementation that also allows you to make HTTP routing apps as well as command line interfaces, all the same thing. So it's going to be pretty fun. And if no one else has any announcements, you're free to go.